So let's welcome the next lecture of MAT-601, that is real analysis 2. So in previous lecture, so we have seen, just to revise it. So first we define open sets. So what's the definition of open set? So capital M be a metric space and a non-empty set G of a metric space M is called open in M. So when we say capital G is open in M, if for every x belongs to G there exists number positive real number r greater than 0 such that the entire open ball, so open ball dot x with radius r is totally contained in G. So it is true for every every point of G. So this is the definition of open set in metric space. So after that we have seen, so every open ball is an open set. So open ball itself forms an open set. So that's why that word open is there in open ball. So its solution we have seen. So you can consider it as theorem. So after that we have seen one note, that is every singleton is open set in discrete metric space, that is RD. That is singletons are open in RD. So after that we have seen some statements of theorem. So first theorem, that is in any metric space M row, both M and the empty set phi are open sets. So basically these are the trivial open sets in any metric space. So second, let F be any non-empty family of open sets and a matrix M in matrix M, then collection of all these open sets, that is union of all these open sets, is also an open set subset of matrix space M. That is countable union of open sets is again open. So you can alternately you can write it as, that is, see, that is countable union of uh, yeah, countable union of open sets is again open. So that is the statement of this theorem. So after that we have seen, let me put, so okay, yeah, every subset of RD is an open subset of RD. So obviously how it is, so we have seen when it is finite, then you can write every finite subset of RD as union of singletons, and if it is not finite means it is countable. So in that case you can write, so every countable subset of RD as union of countable number of singletons. So obviously, so using previous theorem, so every subset of RD will be open in RD. So after that we have seen one theorem, that is if G1 and G2 are open subsets of matrix space M, then their intersection is again open. So that was the previous theorem which we have proved also. So that was the proof of this theorem. So next theorem. So let's suppose, so M1 row 1 and M2 row 2, T2 matrix spaces, and F is a mapping from M1 to M2. So then F is continuous on M1 if and only if, so inverse image of G is open in M1 whenever G is open in M2. So F is a mapping from, suppose, M1 to M2. So then, so this will be alternate definition for continuity or continuous function on matrix space. So F is a mapping from, see, so F is a mapping from M1 to M2. See, is there? And if G, so when we say this mapping is continuous mapping, so if F is continuous, then this statement is true. That is, so whenever G is open in M2, so its inverse image, that is F inverse of G, should be open in M1. And if it is true for every open set G, if G is open in M2, means whenever G is open in M2, so its inverse image is open in M1. That is F inverse of G is open in M1. So it, so converse part of this theorem. So it implies that, so F is continuous on metric space M1. So that is another definition of continuity on a metric space. So next, yeah. So briefly we can summarize this theorem as, so F is continuous if and if the inverse image of every open set is open. So this is about open set, so which we have seen already in previous some lectures. So next topic, that is closed sets. So first we will see definition of closed set. So before that, so first we will see definition of limit point. Yeah. So this is definition of limit point. This problem. Just a minute. Yeah. Yes. So this is definition of limit point of subset of metric space. So this is definition of limit point. So let capital E be a subset of metric space M. So a point x belongs to E is called a limit point of E if there is a sequence x of points in E which converges to x. So when we say capital C, small x is limit point of capital E. So let us see. So there should exist, whenever x is the limit of E, so for this x there should exist sequence of points in E, so that that sequence should converge to x. So in that case we will see x is limit point of subset E. So capital M is a metric space, capital E is a subset of metric space M. So when we say small x, which is the element of capital E, is a limit point of set E. So if there is a sequence xn of points in it, so it should be sequence of points of E, so that sequence should converge to x, means that x should be limit of at least one sequence of points in E. So obviously in that case we will see x is the limit point of E. At least one sequence of points of E should converge to this x. So this set of all limits points of E is denoted by this notation, that is E bar. So we'll write it as E bar. So what is E bar? E bar is set of, yeah, sorry. The set of all limit points of E. So we'll denote the set of all limit points of E by E1. So if capital E any subset of metric space M, so obviously always cap, so that set E will be subset of E cap E bar. So that set is always contained in the set of all limit points of that set E. So this is about, so limit point and set of limit points of subset of metric space M. So next definition, that is the definition of closed set. So when we say capital E is an closed subset, let us see. So when we say capital E is an closed subset of matrix space M. Just a minute. Yeah. So let E be a subset of matrix space M. So we say that capital E is closed subset of M if the set of limit points of E and itself both are equal. So if E is equal to E bar, then we will say E is closed subset of M. So that is, you can write, see, capital E is closed subset of M if and only. So capital E is equal to E bar. So this is definition of closed subset of matrix space M. So note that to prove subset E of matrix space M is closed, it is enough to show that so E bar is a subset of E, because just we have proved. So E is always contained in E bar. So it is there. So obviously to prove that, so E is a closed subset of matrix space M means E is capital E equal to E bar. So it is just to prove E bar is a subset of E, because E is always a subset of E bar, just we have written. So next, yeah, again there are some theorems and we will just state these theorems. Just a minute. Yeah. So let capital E be a subset of matrix space M. So then the point x belongs to M is a limit point of E if and only if every open ball about x with radius R contains at least one point of E. So let's see. So it will be alternate definition for limit point of an set. So let capital E be a subset of matrix space M. Then the point x belongs to M is a limit point of E if and only if every open ball about x with radius R should contain at least one point of E. So in that case, so we'll see. Say x is an limit point of E. Means if we draw, see, any open ball about this point x should contain at least one point of this set E. So this is another definition of limit point of set. So next theorem, if capital E is any subset of matrix space M, so then E bar is closed. So this E bar is always closed subset of M. So whatever E, so E may be closed or not closed, but always set of limit points of E will be closed subset of matrix space M. So that is, so what is the meaning of E bar is closed in M? It means that so E bar will be equal to set of all limit points of E bar. So that is E bar E double bar. So E bar will be equal to E double bar. That is, you can write. So next, in any matrix space M row, this sets M and phi means, so capital M and the empty set are both closed. Already we have seen in any matrix space M row, the sets M and empty sets are both open. So here we state that so M and phi are always closed as well. So that is, you can write. See, in a matrix space, M and, you can write matrix space M row. So M and phi are both closed and open. So this statement of this theorem. So we'll combine previous statement and this statement. So right. So both M and empty sets are closed and open. So these are trivial open sets and closed sets in any matrix space. So next theorem, yeah. So yeah, if F1 and F2 are closed subsets of matrix space M, then their union, that is F1 and F2, is closed subset of M. See, so it is always true. So next statement, that is, let G be an open subset of matrix space M, then G dash means complement of G, that is M minus G, is closed. If G is open, then its complement is closed, and if F is closed, then its complement, that is G minus F, is open in matrix space M. So that is, you can write. See, if suppose G is open, implies that G dash is closed, and see, so F is closed, implies that so F dash is open. See, G dash means complement in M, means what is that? That is F M minus G, and what is F dash? That is M minus F. So it is always true. So next theorem, yeah. So let M1 and M2 are two matrix spaces, and F is mapping from M1 to M2. So then F is continuous on M1 if and only if. So inverse image of F is closed subset of M whenever F is closed subset of M. So this is same theorem which we have just seen for open sets. So this is another definition of continuity. See, so alternate definition of, so it will be alternate definition of continuity. So when we say F is continuous mapping from M1 to M2, if and only if, so see, F inverse of F is closed subset of M whenever F is closed subset of M2. So next definition, that is definition of dense set. So when we say, see, subset capital A of matrix space M is an dense subset of matrix space M. So if closure of A is equal to whole matrix space M, so this is the definition of dense subset. So let M be a matrix space and A is subset of M. So when we say capital A is a dense subset of M, so if A closure is equal to M, means close A, that is set of all limit points of A, should be equal to whole matrix space M. That is, A is dense in M if every point in M is a limit point of A. Obviously, yeah. So this is meaning of A bar is equal to M. So every point in M should be limit point of A. That is, A bar should be equal to M. That is, set of all limit points of A should be equal to M. So this is the end of the chapter. That is, yeah. So in the chapter, what we have seen, just I will revise. Yeah. So title of the chapter was continuous functions on matrix spaces. In that we have seen 3 points, that is functions continuous on matrix spaces, second open sets, and then closed sets. So in first, that is 2.1, so we have seen so many form of definition of continuous function on matrix space. Second, that is 2.2. So in that we have seen definition of open set and so many theorems on open sets. And in 2.3, so we have seen definition of limit point of a set, then definition of closed sets, and then so again uh, different theorems on closed sets, and again theorem on continuity of function. So this is the end of the chapter. So next chapter, yeah. So third, that is third chapter. Title of the chapter is that connectedness, completeness, and compactness. So in this chapter, we will see. So there are total 7 points. First point, that is 3.1, more about open sets. So again, we will see. So some more properties of open sets in this first point. So in 3.2, so we will see definition of connected sets and some theorems on connected sets in matrix spaces. In 3.3, we will see definition of bounded set, then definition of totally bounded sets, and some properties of bounded sets and totally bounded sets. So in 3.4, we will define complete matrix space and some theorems on complete matrix spaces. So in 3.5, we will see compact matrix spaces. Again, so some properties of compact matrix spaces. In 3.6, we will see continuous functions on compact matrix spaces. So again, we will see certain forms of definition of continuous function on matrix spaces, and last we will define uniform continuity. So in 3.7, there is just definition of uniform continuity and one so main theorem of uniform continuity. So this is chapter number 7. So we'll just continue. So next lecture we will continue chapter 3, that is first point of chapter 3, that is 3.1, more about open set. So we'll stop here and we'll continue remaining part in next lecture.